Thank you for joining us. Before you join us, we reviewed the laws of motion as formulated by Sir Isaac Newton, types of forces encountered in mechanics. Topic today, unknown, mystery. Didn't tell my students. We'll figure it out as we go. You caught us in trying to answer a question for which we have a good laugh. Why don't we sink through the floor? Why my students are still sitting on their chairs, not passing through? Why this block takes the whole earth to pull it, but the desk will stop it? Yes, Bob, what are the dots? Yes, they are atoms. I'm trying to explain quickly what is the nature of the normal force. No, it's not the topic of today's class, but it's very close. We're getting hot. It's related with what we want to discuss. So, in very, very simple model, red atoms belonging to a block, black atoms belonging to the surface, you bring them together. Please tell me. Very good. What? Electromagnetic repulsion. It might be early, still early for us to understand what means electromagnetic, but you understand the atoms are coming too close to each other. We don't see this cushion as invisible. Believe it or not, you are floating on your chair on that cushion. Sum all the arrows up, I get what? Bob, thank you. Normal force, which is explaining why the block is not going through the table, although there are immense empty spaces between atoms. What are the red arrows? You say, wait, let's vote. It's a big class. Use your remotes. I see the results. Most of the class still says, wait. But, yes, I have some voices saying, very good. And that's correct. Reaction to that. It should be normal force. Remember what we've discussed about the force which is read by the scale? It's not necessarily your weight unless you stand still. If you dance, if you move in an elevator with acceleration up or down, it's not going to show your weight, more or less. It's the normal force, which is basically the pair of what's acting up. If you have a rest, then you can say it should be the same as the weight. So the summation of the red, which are correctly normal forces, are still called reaction to the first action, but they can be equated with weight. Question: what will happen if I continually push an object and at some point give up? It will definitely stop. If I launch it, it will stop. Yes, common misconception, we discussed that, just reviewed law of inertia. Voyager 1, yes, Voyager 2, they don't need the force to keep on moving in space because there is no, yes, that's the magic word, thank you, friction. That's the mystery topic today, friction force, which might explain for this block why it stops. This is a small hovercraft. Why doesn't? Like Voyager, continue to go at the same pace. Why? Because the friction force is almost zero, denied by that cushion of air. Otherwise, there should be a friction force which appears to move, to be impeding the motion. The topic of our class today. So, Yes, if I push on an object and it doesn't move, I still have to explain why it's static. I'm pulling and I can read my action and it's not moving. Probably because there is a static, not moving, friction, which will match my push or pull. Visible, red, F, invisible, friction force, static. What will happen if I increase my force? See, different readings, still not moving. Yes, you're right. The friction force will always match the push or a pull. Why? Anna? Sure, net force 0. Explain rest. True. What if I go beyond the threshold? Keep on pushing, or pulling in my case. Look at the needle, look at the needle. What happened? Oh yeah, while I'm moving, the needle shows less. It conveys, we'll call it forward motion, kinetic, and it appears to be less than the maximum friction force, static, for not motion. So in this case, the friction appears to impede the motion. Yes, Meg, you are true. Professor, she asked, but you are walking. Yeah, I'm walking. Yeah, because I have a good grip on the floor. And it doesn't impede my motion. Actually, it explains my motion. So in this case, or for a car driving on a dry pavement, the friction force is the one explaining the motion. In this case, the friction impedes. It's against the motion, the action from outside. Let me show you again on this video what I just did in front of you. Static, increasing, friction force matching, reaching the threshold, the needle jumps to a low value. Yes, please summarize for me, Selma. Friction force, kinetic, will be less than the maximum static friction force. That will be something we'll also check in our next lab. Please give me examples. I will go quick through this, assuming that I'm getting a lot of examples, adding my own examples. Grip, normal force, push, creating a static friction force. We don't want to slide. Talking about sliding, ice, you need better shoes, crampons, sweaty hands, slippery hands, no slippery hands, good grip. You take a glove, clips, a bar. I will do this in class quick, hold the bar. Apparently I'm able to do that. Then take some oil and show the student that the bar will slide through my hands if I do not have enough grip. Motion, static, friction forces are present in both cases. I will give the example of what means skidding. Yes, my students ask me about ABS. I will explain what is that, why, turning the wheels, pumping the brakes much quicker than we can. The computer of the car doing that will allow us to have a shorter stopping distance, not freezing the wheels as we brake. I will probably stay in class longer and discuss those examples. And I will say, yes, physics is relevant to your life. Please connect to your everyday life. because this is how you really make physics to be meaningful. Taking a closer look, as we did for the normal force, yes, my students will say, but it looks flat, it looks smooth. I agree, but again, let's zoom in and we'll see this: mountains, valleys, landscape. The friction force can be explained in the terms of the interlock between those imperfections of the two surfaces. The blue, the top object, the block, the red, the surface underneath. One example will be, that's why it's hard to unstuck something, make it move, because basically the blue will have to climb all the way to the top of the mountains. And then it's easier to just jump from one mountain to the next, moving, than it was to climb from the bottom all the way up. Again, similar to what we've done for the normal force, atoms, blue, the block, red, the surface underneath. If we consider the atoms which are directly opposite to each other on vertical, we can relate to the two normal forces, the two action and reaction. If there's no motion on the perpendicular direction toward the surface, then normal force and weight of the block are equal to each other and opposite. But what if we push the block, which has the tendency to move toward the right, then in general atoms will try, because of the potential motion, will try to repel now on a direction which is neither along the surface or perpendicular, arbitrary angle. And students might say, but professor, you can do this. Yes, I can. Yes, we can. We can project the forces, and projecting the two forces, which in general will define how the atoms are interacting, repelling, because of the electron clouds coming too close to each other. What I get on the normal direction, perpendicular to the surface, I equate with the two action-reaction, normal force, up, down, down being the gravity if I have no motion on that direction, while along the surface, I will equate that with the friction force, which has to be in that surface, along that surface, for both cases if it's static or kinetic. Thank you.